Hello, today we take you through the OCR Gateway GCSE Combined Science Chemistry paper. Now we're going to go through the foundation paper here on this video, but if you're higher, you should go to this link and click on for the higher paper. Now to help me today, we have a special guest, Mr. G. Mr. G? I know how to get him. Chemistry, that's what it is.
That was weird. Anyway, moving on. I'm Mr. G, and I'm going to take you through the chemistry paper.
We'll be shooting our way through this paper within about 15 minutes. But at any point that you want more clarification, just hit that pause button. Here we go. Question number 1. We want to get a solid from a solution. So we evaporate off the solution, leaving the solid. Answer B. Number 2, a carbonate contains carbon and oxygen, hence the word carbonate. Also gives salt and water. C. Number 3, ethanoic acid being a weak acid. You know your pH scale, it has to be from that choice, pH 5, that's B.
So essentially, they want to separate their solid which is dissolved in the solution. We need to get rid of the liquid. Only A is going to actually remove the liquid and leave the solids behind. Well, we know that sodium is in group 1 of the periodic table and chlorine is in the group 7. That means one atom of sodium will react with one atom of chlorine, so we'll end up with NaCl. C immediately jumps out at me. We know that atoms can be subdivided because we know that atoms are made up of smaller things. Protons, electrons and neutrons.
Number 7. Relative atomic mass of 19. Check out the periodic table and we see mass 19. We have fluorine. The lower number on fluorine is 9. That's the atomic mass. It tells us how many protons it contains. So the number of protons is 9A. Number 8. The size of an atom is something in the order of 10 to the minus 10. There's a few minus 10s there, but let's check out some of the other answers. 10 to the minus 6, but that's 0.0001. Move the decimal place 4 places to the right, and that minus 6, we can add another 4 to that to make minus 10. So that would be 1 times 10 to the minus 10, answer being A. Further information on the size of atoms, you can check out this video in the link above. Number 9. Graphite used in pencils. The reason is atoms in graphite are in layers, so the layers can rub off each other onto the paper. B.
Question 10 then shows us a reaction profile for a chemical reaction, and we can see how much energy we have at the start in our reactants, and then it goes up and then it drops down and we see how much energy our products are left with. So we can see that this actually loses energy. If you look, our reactants have about 250 kilojoules of energy per mole, and our products end up with about 150 kilojoules of energy per mole. We've lost overall 100 kilojoules of energy per mole. So, on to question 11. First of all, it tells us to look at the pictures of some common lab equipment. And we've just got several different pictures here, so let's turn over. First thing I need to do is get some ice and I need to crush it up. I'm then going to drop that ice into a beaker and I'm going to stir that ice around just so it's all settled, it's all level and it's all sort of mixed together. I then need to get a thermometer because that's how I'm going to record the temperature. I need to put that thermometer into the ice and I need to make sure that the bottom of that thermometer, the bit that actually reads the temperature, is covered by the ice at all times. If my thermometer is not in the ice, then I am not recording the temperature of the ice. Remember, this needs to be done accurately. I can start to heat that ice gently using a Bunsen burner or a water bath. So I just keep an eye on the thermometer when it melts and turns to water. Then once all the ice is melted, the temperature will start to go up again. Well, as always, one way to improve it is going to be to repeat it. If you repeat an experiment and you prove you get similar results when you do it again, you have made your experiment better. We could also use a digital thermometer.
Now the relative atomic mass is the mean mass of that particular atom. That's compared to 1/12 of the mass of a carbon atom. Here's carbon atom, 612C. The smaller number is the atomic number. It tells us the number of protons in that atom. But since atoms are always neutral, there should be as many negatives as positives, so therefore it also tells us the number of electrons. According to the table below, if we have a proton of +1, an electron should be opposite and equal to that, i.e. -1. Neutrons end for neutral, that end for no charge, that's a charge of 0. Now if a neutron has got a relative mass of 1, protons are approximately the same size, so that would be 1 as well.
Electrolysis is just splitting a solution using electricity, and we use 2 carbon rods. As it's electricity, one of them is going to be positive, one of them is going to be negative. So the positive one is called the anode, and the negative one is called the cathode. And then the solution is called the electrolyte. So we split the electrolyte up using the anode and the cathode by passing an electric current through them. Well, if you think back to what you've been doing since Key Stage 3, when you draw those solid, liquid and gas diagrams, one thing you always say is that in a solid, those atoms are locked in place, they're not free to move, they're stuck. It's the same here. In a solid, those ions cannot move. But once you dissolve it, so you've got a liquid, those ions are now free to move about. And it wants us to complete the table saying which product will form at the positive electrode. So if we look at our first one, we have molten PbBr2. Well, immediately looking at my periodic table, I can see that bromine is in group 7. That means that it is going to have made a negative ion. My bromine atoms want to gain one more electron, so they have a full outer shell, so therefore they're going to be negative, and the negative one is going to be attracted to the positive electrode. So we'd have lead going to the negative electrode and bromine going to the positive electrode. We have a solution of potassium bromide. It does say the product formed at the negative electrode is hydrogen. Hydrogen and potassium are both in group 1. They both have 1 electron in the outer shell. That means they are going to make a positive ion that would be attracted to the negative electrode. And then we have bromine again, so it's the same as our first example. Bromine is group 7. It's going to make a negative ion, or it will be attracted to the positive electrode. And then moving on to the last row, we have a solution of copper chloride. Well, again, it is probably easier for us to look at chlorine, so we know that chlorine is also in group 7, therefore it's going to make a negative ion, therefore it's going to be attracted to the positive electrode.
Electroplating is the same procedure as electrolysis. Here what needs to be plated needs to be attached to the negative electrode, or the cathode. We've got 3 marking points here, but only 2 are needed. The final one being that water would not work. Water would not be able to conduct ions. We need a solution.
We have 2 carbon atoms, 4 hydrogen atoms and 2 oxygens. The empirical formula then just means the simplest ratio we can write that as. So if you divide it all by 2, you end up with CH2O. So we need our periodic table for this one, and we need to find out the atomic mass of these elements. Again, if we look at the chemical formula for our molecule, we actually have 2 carbon atoms. So we need to times our mass of carbon by 2 to give us 24. We then add those masses together, which gives us 60. Write down 2 other limitations of the displayed formula. So one of the problems is that it's in 2D. Some of these atoms might be further forward, some might be behind other atoms. It doesn't show us the size of the atoms.
The electronic structure, here we've got 3 numbers, therefore it's in period 3 electron shells. The last number being 5, so it has 5 in its outer shell. It gives the formula for the final product, so we know there's only one phosphorus and 3 hydrogens. Phosphorus electronic structure 285, 2 electrons, 8 electrons and 5 electrons. We'll do them as dots. Hydrogen, from the periodic table, has got an atomic number of 1 proton, therefore 1 electron. We'll do this 1 electron as a cross. To become stable, it will need 2 for that shell, so it shares the dot and the cross. The phosphorus will share dots and crosses with the 3 hydrogens, so 1, 2, 3, 4, 5, 6, 7, 8 now in the outer shell, full outer shell, all stable and happy. Question 16. So we have the reactants on the left hand side of the equation and the products on the right. Always a good idea to highlight all the important parts of the question. And let's have a look at the table. The question says calculate the mean temperature of experiment D. Mean, we add up all the results and divide by 3. Always a good idea to show you're working. Now describe the pattern of the highest temperature reached for A to C. So if we look down at the mean temperatures, the volume of HCl increases, but the volume of NaOH decreases. Similarly with the pattern of pH.
And it's a 1 mark question, so you only need to put 1 conclusion, but there is more than 1 conclusion that could have been drawn from this data. So there are several answers, but you only need to put 1 to get the 1 mark. So one of the ones you could have said was simply that you got the largest temperature rise at a pH of 7, or when it was neutral. So when this solution was neutral, you got the largest temperature rise. That would get you 1 mark. Similarly, you could also say that you got the largest temperature rise when the same amounts or the same volume of hydrochloric acid and sodium hydroxide were used. You could have said the final solution is neutral when the volume of acid and sodium hydroxide were equal. So when you put the same amounts of both in, you ended up with a neutral solution. That's another conclusion you have drawn from the data.
3, 2, 1.
Well, thank you, Mr. G. There's actually quite a number of answers we've not gone through yet which are permissible. If you reckon you got a good answer, which were not mentioned, check the final mark scheme or ask your teacher. Now with chromatography, the RF value is the distance to the spot divided by the distance to the solvent. This is all from the pencil line down the bottom. So we can measure it using the distance up the side. The solvent is, in each case, goes as high as 8.8 centimeters. And we get the values for spot 1, spot 2, 3 and 4. Now looking at the table of pigments and RF values, first of all, spot 4 is 0.95. Looking at the table, that is going to be pigment A. We've got spot 2 here at 0.31 or 32. Looking at the table, that's going to be pigment C. Now, spot 1, 0.125. Well, there is a 0.15, but it's not precisely, it's not a close match. And for spot 3, 0.648 isn't on the table at all.
And the question now asks us to describe and explain which pigments are in the sample from the plant and suggest why further analysis might be needed. So just to go through what we've just done, we have just calculated the RF values for the 4 spots we have on our sample. And we have some values for pigments that have been given to us. So we can compare our values that we've calculated to the example values for certain pigments we've been given and see if they match up. So if we look at spot 1, we calculated our spot 1 value, RF value, as being 0.125. The closest to that on the list is pigment E with an RF value of 0.15. So it's possible that our spot 1 could be pigment E, but it's not close enough to say so conclusively. So spot 4, we calculated our RF value as 0.955. And again, looking at our table, we actually do have pigment A, which we know has an RF value of 0.95.
Now we come on to the last 3 questions, also appear in the higher paper. Now here, we need to explain why the nanotubes are so strong, using ideas about bonding. There's 2 marks for this one. Many strong, and they're covalent bonds. And for B, we need to explain again. One to say they're delocalized, the electrons, and that they're free to move.
Well, to find out how many more times dense the iron is in the carbon, we just divide the density of the iron by the density of the carbon. It is important here we show our workings out. It's a 2-mark question. If you show that working, even if your answer is wrong for some reason, you will still secure 1 mark. Well, if something is dense, it means that all the matter are packed together as tightly as possible. In carbon nanotubes, there are really strong covalent bonds. You have to break some of these bonds if you want to turn it into a liquid. Because the bonds are so strong, it takes a lot of energy to break those bonds.
The aluminium needs 3 electrons to balance out the 3+, oxygen needing 2 electrons to balance out the 2 negative. So we can multiply the 3 negative by 2, and we can multiply the 2 negative by 3, that will give us 6 in each case. Equal aluminium ions, and the 3 oxygen ions would make the formula. Mg, that's going to be 2+, and NO3 is 1-. So we're going to need 2 lots of the NO3 negatives to match 1 of the magnesiums. Three chlorines on the right hand side, so we need 3 on the left, but 2 aluminiums on the left, so put 2 in front of the aluminium on the right. But that makes 6 chlorines on the right, so change to 6 chlorines on the left. But now there's 6 hydrogens on the left, but only 2 on the right. So we'll put 3 here to make it 6 hydrogens. We also now have 3 sulfurs on each side. Room temperature is about 20 degrees centigrade, so that is well above the -60 boiling point. It is a gas.
So that brings us to the end of the chemistry paper. We wish you all the best. If you have any questions or comments, please leave them in the comments below. Thank you.
Thank you, Mr. G. And I'm off now to perfect my chemistry.